Okay. Today we're going to talk about two things. We will talk first about power electronics, and we'll start off, hopefully everything will come together here, because this is my favorite demo for the class, but we'll start off with the demo. Hopefully everything will go right. And then we'll talk about, if we have time, we'll talk some about power flow too, which is essentially how we get power from generators in the grid, large-scale generation systems, to actual substations for distribution, how power actually moves over a transmission grid. As I said, we're going to sort of finish up this kind of units kind of hopping back and forth in terms of various pieces of power systems. We started, remember, with a little bit about generators and how those work. Then we'll talk a little bit about three-phase power, which is how power is distributed on the grid as a whole. And now today we're going to talk a little bit about power electronics. To motivate this, a little bit about power electronics, I want to start off with some demos here. So if you're like me, you took a course in AC circuits, and you figure, oh, well, you know, power in the US is AC. We get our power from AC systems, so I know what those look like. You know, you'll have sine waves that get shifted from each other, and this is what power in a home or in any kind of device actually looks like. And then I started looking at actually analyzing power in some, for example, home systems, and I was sort of surprised at what I found. So rather than tell you, I'll just actually try to show you. Hopefully this will show up in good enough resolution here on the board, and hopefully show up in the video too. But I want to demonstrate a little bit about what power and electricity actually looks like in a system like the various electronics we have here. So this demo has many different components to it. And I'll try to go through them one by one. What I'm going to do is I'm going to be plotting the waveforms from voltage and current from real devices here. So we have a light bulb. We have an LED light bulb. I'll use my iPhone here. We'll see what that looks like. I have a hard drive. We can look at this computer, what it looks like, in kind of a cyclical way. If you're looking on the computer, what the computer looks like, that's kind of fun. But we'll see what it actually looks like, because it's not sort of what I expected when I first saw this. Maybe if you guys know what's going to happen here, maybe it'll be expected for you guys, but it wasn't expected for me when I first saw this. All right, so to start off with, let's look at what voltage looks like. So that's actually kind of a nice one, because voltage ends up being pretty nice in most places. Remember, voltage is supposed to be a sine wave that goes at 60 hertz, right? So the period of the sine wave is 60 hertz in the US. So let's actually see what it looks like. So here I have a voltage transformer. It's essentially a probe for an oscilloscope for high voltage situations, but I cut off the probes that you normally clamp to wires, and I just put a little plug on this. So what's going to happen is that we're going to plug this in here, and then what's going to come out here is a much stepped down version of that same voltage pattern. So we can actually see what it looks like, and then I'm going to plug it into this little guy here, which is an A to D converter, analog digital converter, which will convert that voltage signal to a form the computer can read, and then I'm going to plot what it actually looks like. Okay, so these are, actually this is kind of an expensive one, but you can buy these pretty cheaply. All right, so let's hook it all up here and see what happens. So I'm going to plug in my A to D converter. There's so many things that could go wrong with this, but hopefully it'll just all go right. I'm going to plug in this guy here to an outlet down here. So now it is taking that voltage from there, stepping it down, actually 100-fold. The actual amount doesn't matter, because then it's just to an amount that this guy here can actually read. If we put in 120 volts into this, that would actually probably break this. Actually, it wouldn't, again, break this one because this was a pretty expensive one, but it would break a lot of cheaper ones. So I'm going to plug this in, turn it on, and see what it looks like. And hopefully everyone can see this. So I'm going to run this little script here called voltage. So actually, it has to make sure that I found it first. This not successfully installed. What? I just used this before. See, I told you everything can go wrong here. Yes, okay, that came up. All right, so let's try to see what this actually looks like now. So this is going to now plot a picture of the voltage. on the scale of voltage itself. There's a little bit of jitter. Don't worry about that. That's really just because I'm looking for the spot where it crosses 0, and it varies by a fraction of a timing step in the resolution of the graph. But this is what the voltage looks like in this circuit right here. Really, all of these circuits, they're all connected. So that's sort of what you expect, right? And this axis here is voltage in volts, and this axis is actually its number of samples. So this goes under 160 hertz. So 160 hertz, we're getting about 200 samples or 250 samples or so. What's really happening is we're sampling this at 16 kilohertz. So we're sampling this voltage pattern at 16 kilohertz out of this guy here, and then we're plotting what it looks like. So you only sampled it once or twice a second, you wouldn't be able to see this at all because, of course, it goes up and down 60 times a second. But we're looking at it in very, very high resolution here. Actually, you can go higher if you want to and do some really crazy stuff. But we're a reasonable resolution here. And we can see this actual voltage signal from the outlet here. And it's not I guess perfect. There's some things where this is not quite a perfect sine wave, but it's pretty good, right? This is sort of a pretty good sine wave here. As we expected, the maximum is at about 170 something. That's what happened there? Oh, I just went to sleep. My computer just died. Wonderful. This is actually a bad thing, because I think I might have my charger elsewhere. So I might have to go back and actually do this, because I need this computer, and it apparently just died. Oh, no, this is plugged in. What's going on here? No, I have it here, so it's just weird, actually. It is plugged in. I don't know what's going on. We'll see. I've been having some issues with this laptop, too, so hopefully things go well here. OK. All right. Let's try this one more time. Maybe my little program here caused the entire computer to just shut down. I guess that's possible. I know it also went to install some updates for a long time, but I think it just actually went ahead and shut down, so I'm not quite sure what happened. So anyway, what you saw in that graph there, right, that makes sense, right? That was the voltage signal from this system. So it's this sort of nice sine wave that you kind of expect to see. In a second, yeah, now it's applying all these updates. OK. Well, we'll wait a little while. Does anyone have any questions about what you just saw? Yeah?
Should the max be 120?
Right, so this is what we mentioned before in class, remember. The voltage in an AC circuit is 120, but that is actually talking about root mean squared voltage. So that's if you take that whole signal and multiply it by the root mean squared value of it. So the actual voltage is square root of 2 times that. So, or was it square root of 2? Yes, square root of 2 times that. So the peak voltage of a sine wave, just by relations of sine waves themselves, is the square root of 2 times the root mean squared. That's just a property of a sine wave itself. It only holds for sine waves. So the max there is going to be 173 or so, not 120. The root mean squares, whenever anyone reports, and this just shut down and started up a different OS. Awesome. Right, so what it shows there is actually the root mean squared voltage, not the absolute value. Sorry, what you hear when you talk about 120 volts is the root mean squared voltage, not the absolute voltage. All right. OK, so let me just explain what I'm going to do next, actually, while this is all getting set up. So what I'm going to do next is look not just at the voltage, which is subscriptance, but actually at current waveforms now. And the way we do that, it's a little harder. Well, it depends what you call harder or easier, actually, to look at voltage or current. So what we're going to do with current is we don't really want to put something in line with the circuit that measures the current. That's just a little bit dangerous. I mean, I guess I could do it for some little thing like this, but when we're measuring the whole building, we often don't want to put things in line with the current to measure it. Certainly, I wouldn't want to take off the entire main voltage supply of the building. So what we use is something very nice that AC systems allow us to do, which we use something called current transformers. So one very nice property about AC electricity is that if you run a current through a wire and then put a magnet around that wire or some loop of wire around that wire, Remember, a changing magnetic field, changing electric field will create a magnetic field, which will in turn create an electric field in a loop of wire around that wire. So what we do here is we essentially just take an AC wire and we put a little clamp around it. So this is a circuit transformer that we use here. And what that does is that creates any current that travels through that wire, this little hole here, will create a voltage difference in the end of this wire, which we then can similarly read in our little A to D converter there. And so we can use this to actually plot the waveforms of the current we see, not just the voltage. All right, so I'm going to try this one more time. Hopefully this all goes off without a hitch this time. So what I'm going to do is I have this little wire I created here. So what it is it's just a wire, extension cord that I cut open. And I'm going to put this current transformer around one of the wires here. It's important you have to put it around one single wire. You can't clamp it around the whole wire. And the reason for that is that any current that flows one way will also flow the other way if you clamp it around the entire wire. And those two will cancel. So there will be no net magnetic field around this wire as a whole. Only if you actually break it open and put it around one of them will you see any type of current like that. So I'm going to take this wire I cut open and put this little current transformer around the wire. And then plug it in. I guess I should plug it in, well, maybe over here. Maybe we'll have room for it. Now I'm going to plug the other end into my A to D converter. OK, now let's see what this looks like if everything stays reasonable here. Where was these? OK, just check to make sure the voltage is still working. Of course, unless this was the one that crashed it before. But we'll see how it works here. So this should be the same voltage picture as before. It takes a little sec to start up, apparently. But we will see. Maybe I should have to unplug this and re-plug it back in. Come on, come on. OK, there we go. Here's our voltage back. All right. So voltage looks the same. Remember, now what I've done is I've plugged in this current transformer to a wire. And what I'm going to do now with what this picture here actually shows is the following. I'm going to take these current waveforms and actually synchronize them to the voltage. So as you'll see in a second, it isn't always easy to find that sine wave for current signals. But what you can do then is actually sort of look at these at the same time and just draw the corresponding current waveforms for that sine wave of voltage you saw before. So that's what I'm going to draw now. And we'll see how this goes. OK, so right now it's just garbage, right? Because nothing's plugged into here, obviously. We don't have anything plugged into our circuit. Now let's start plugging things in. So let's see what the current looks like. Remember, we're looking at current waveforms now, not voltage anymore. And we'll see what those look like for various different devices here. So here is sort of the simplest one we can have, right? It is a incandescent light bulb. Let's see what this looks like when we plug it in. Get into the current signal. OK. So there we go. That's what the current waveform looks like now for this light bulb. There's a little bit of noise, especially might be caused by this whole chain of stuff that I have going here, more than the light bulb itself, or just actually noise in the actual sensor itself. That's actually probably the more likely thing. We're talking about relatively small amounts of current here. So this is 4 amps, 0.4 amps of current to power this light bulb. This light bulb is 40 watt, and so this makes about amount of sense, right? Because if you look at the root mean squared value of the current times the root mean squared value of the voltage, that would actually be the apparent power of this thing. But because it looks like it's pretty well in phase, the voltage and current are pretty well in phase here, this is about 40 watts of power this is consuming. Does all that make sense? Yeah, there's a question there.
In normal outlets, you just have two, how do you call it? There are two electrode.
Two prongs, yeah.
Yeah. But there should be
Three? So three-phase power you're talking about, right. So what actually happens is that a home, for example, will actually typically only get one of these three phases of power. And certainly any outlet will actually get one phase of power. It's actually a little bit complex what happens. So three phases all sort of come out on the transmission lines. But on any given house, actually, usually they only tap one of those three phases. Some bigger buildings will actually tap all three of them. And for some bigger devices, they actually make a lot of good use of all three phases of power. But most homes will actually just use one of those phases of power. When it comes into the home, again, if you haven't heard about this or don't know sort of the story here, don't worry about it. But actually, sometimes, or actually often in the US, you'll actually have two phases of power in a home. And so you'll have two phases that are 180 degrees out of phase. And what's actually happening here is that these is actually still just tapping one of the three phases of power on the transmission lines. But then when it comes to your house, you actually tap it in two different directions, and you get two phases of power that are 180 degrees out of phase. And so that's how you actually get some amount of power that is 120 and some that is 240. The 240 things will use both those two phases, and the 120 will just use one of the phases. But for the majority of the time, you are only seeing one phase of power or one of those three phases of power in what you see. Now, the two prongs in an outlet there, what they are is those are essentially input and return wires. So one of those wires is actually where the electricity comes from, and one's just connected basically to take a return. Probably not all the way back to the generator, because that's why you sort of use three-phase power, so you can connect them. But in the house, you might not have perfectly balanced power in the different phases, so you actually want to have some return line that will go out to the street and do all this kind of stuff. So, or maybe actually even just the two phases sometimes come together and have a ground and go to the ground after that. So that's what those two wires are there in an outlet. The third one just being a ground prong that actually is mainly there for safety too. But right, these two little prongs here are one phase of power that is then furthermore split into two phases of power, and we're just seeing one of those. We're just seeing that when you see those two outlets there. Does that make sense? Yeah.
Going back to what you said before, though, you said that you're constructing this graph by centering the sine wave at 0. So how can you conclude that it's actually in phase with the voltage?
Oh, I see. So I'm actually synchronizing it to the voltage sine wave here. So what I'm drawing here is behind the scenes, it's also looking at the voltage. They're very different scales here, so I didn't want to draw them both. It just kind of confuses things a little bit. So I'm just drawing current here. But actually behind the scenes, what I'm doing is I'm looking at that voltage. The voltage thing is still plugged in here. I'm looking at voltage, and I'm actually plotting this starting where the voltage crosses 0 and ending where the voltage again crosses 0 here. So actually what's happening is that if this looks like a sine wave, then it is in phase. If it were something that was shifted over, that would be out of phase then. If it was 90 degrees off from this, it would be out of phase. But yeah, I'm drawing this synchronized to the voltage. And yeah, right. Okay, so this sort of makes sense to us, right? This is a light bulb. It's one of the simplest loads. It's a purely resistive load. And so all it does is create a current waveform that is in phase with the voltage. Yeah? The x-axis here is the number of samples, so don't worry about that too much. That's what I sort of mentioned before, is that we are sampling little samples from this current waveform very, very frequently. So remember, this is happening 60 times a second. It's doing this. So what I'm actually doing is I'm sampling this 100 or 250 times per that 1/60th of a second. I'm drawing that many samples from this A to D. And that lets me actually see what's happening in very, very high detail here. So this isn't actually that important. What it really should just be is one of these things here. This would be 1/60th of a second after one phase like this. Okay, so this looks reasonable. Let's try plugging in some other things. So again, now we're back to nothing. Let's try plugging in my phone. Does anyone know what this is going to look like, actually? So, you know, when I was first learning this stuff, I sort of figured, oh, you know, maybe there'll be some reactive power. Maybe it'll still be a sine wave. There'll maybe be some, you know, shift, because maybe my phone's kind of a weird device. It might have have some, cause some phase angle difference again, but let's see what it actually looks like. So that's the current waveform. Okay. So what on earth is going on there, right? Looks nothing like a sine wave anymore. So we'll find out in a second exactly what's going on. Remember, this is what the current draw at the wire here looks like when I plug in my phone. So now how do you even talk about things like phase angle with this, right? It isn't a sine wave anymore. This sort of caught me off guard when I first saw it, because you sort of think of AC power and AC circuits as, okay, there's magnitudes, you can have more or less current by changing the resistance, you can shift the current some by changing the impedance. I guess you change both things by shifting the impedance, but this just looks bizarre to me. So what's going on here? So let's look at a couple more things. And what we find is that in a lot of devices, this is kind of more the norm than the exception. So let's look at not actually quite like this, but let's look at a couple other things now. So let's look at actually this computer. Again, that seems somehow bizarre, but it's not actually weird at all, right? Everything's being powered here. Okay, there's this computer. That's kind of strange too, right? It looks kind of more like a sine wave, but it has this weird kind of notch here. And this isn't quite zero current that it's drawing there. It's sort of, yeah, it's kind of strange what this is doing, right? Let's look at this LED light bulb too. So let me plug that back in so it doesn't start complaining. Okay, LED light bulb. Where did my little holder go? Oh, here it is. So these are these much more efficient things, remember, that are going to save about 5 times more efficient. They're going to save so much energy. And here is what this looks like. Sorry for the jumping around. I'm just actually recentering the axis, so it's dynamic, but that means it jumps sometimes when it's kind of noisy like that. So, okay, this looks a little bit more like a sine wave, but it's actually kind of like rounder than a sine wave, right? And it has these little notches here. Sort of unclear why it has those. Okay, try one more, just for fun. Let's try this hard drive. Oh, the other thing is the actual amount it consumes, notice. The other light bulb that was about the same brightness of this, or actually a little bit less bright, was 0.4 there, and this is 0.1, so 4 times more efficient, at least. Probably a little bit more than that, actually, because it's lighter, too. It's brighter, also. Okay, let's just do one more for fun. I like doing these. Let's plug in this hard drive. And this one's fun because you'll actually see it change as the hard drive starts up. So you'll see it change a little bit. So we have something like that. The hard drive is going to start up. Is it starting up now? There, and it goes like that. Now it's spinning. So a little bit like the phone, right? Something going on there that's clearly similar in both those two things. But it will actually, when it's starting up and when it turns on, there's these two different modes here. One's like this, and then when the disk spins, it's actually a little bit different amount of power here, so it changes what it actually looks like. But this is sort of the steady mode when it's not doing anything. I don't think I can actually hook it up to start writing. I don't have that many more wires here, but oh well. You saw a little bit when the disk was spinning, right? It looked a little bit different than this. There were a few more bumps here. And that just sort of stays like this all the time. All right, so again, what on earth is going on here? This looks nothing like what I expected to see when we talk about AC power. So what is actually happening? And what's happening are nonlinear circuit elements here. So the reason why, even with sine waves, we call things linear, is that even though you have sine waves, all that's really happening is you're shifting these sine waves around, you're changing their magnitude, and that kind of things. And you can write these all as linear systems, because they preserve, if you put in a sine wave, what comes out in the current is a sine wave too. And that means you can, and that actually, well, doesn't mean you can do it, but it corresponds to the fact that you can write all these equations out as linear systems. Now they're complex numbers now, but you still have voltage equals some matrix Z times current equals some matrix Z times the voltage, some impedance matrix times the voltage. That's backwards. Voltage equals current times the impedance. So that's sort of the nature of the linear systems. the problem is there are other things you can do to current other than just these linear elements, this resistor, this capacitor, and the inductor. There are more things you can do to them. And in fact, we live in a world where virtually everything, or most everything we have, does this kind of stuff to power and electricity. Because whenever we're powering electronics, for example, we typically actually do use systems that will somehow mangle the current. My laptop here doesn't take AC electricity as its input. It takes DC power. It's much easier to use direct current at some lower voltage. So it's doing all sorts of things to convert AC to this DC system, to this DC voltage source. And that kind of stuff actually wreaks havoc on these current signals that we actually see. So let's talk a little bit now about exactly why this is happening. And I'll go back to, but keep that picture in mind, because we'll see something very similar to that coming up. Here we go. OK, so let's talk now about, skip through all we saw last time. Let's talk now about power electronics. The simplest kind of power electronics, what they're doing fundamentally is they're converting between different types of electricity. And what you saw, or different, say, voltages of electricity, different qualities of the voltage and current. And what you saw in those pictures, you'll see shortly again, and you'll see that it's in fact caused by how we go about converting AC to DC power and things like that. So that you'll see that exact little spiky pattern. You'll see it again, and this is what's causing it there. So we have two kinds of power, right? We have AC power and DC power, and AC circuits and DC circuits. And what we need are ways between between all of these things. So when I say AC-AC conversion, what I mean is actually changing voltage in an AC system. And similarly, DC-DC, we're keeping the same direct current system, but we're changing the actual voltage of a system. So you can do this all four ways, right? You can change AC power to other AC power, or AC current voltage to other AC current voltage, but say change the voltage. And we do that with something called a transformer. Now, transformers are actually not usually called power electronics because transformers actually are all still linear. So transformers follow linear relationships. They just basically exchange current and voltage by some ratio. They keep power the same, but they will maybe give you higher voltage with lower current, for example, in a wire. But these others here, going from AC to DC, which is something called a rectifier, that requires a little bit more detail there, or sorry, a little bit more mangling with the actual waveforms. And all these other ones here actually do require non-linear elements to a system. And collectively, they're called power electronics. So a system that goes from AC to DC is called a rectifier. Something that goes the other way from DC to AC is often called an inverter. Sometimes actually all of these are in various times referred to as inverters, but I'll just call DC to AC the actual inverter, just to be a little bit more clear with notation. And then there are things that go from DC to DC systems, but again with different amounts of precise voltage and current for those DC systems. And these three all use elements that do not preserve linearity of these circuits. So if you put in a sinusoidal voltage waveform, the current waveform here that you get out will not be sinusoidal. I guess that doesn't really make sense for these two, because we start with a DC circuit here. But these also use some pretty fancy electronics to actually convert, say, a constant signal to an AC signal that actually starts to oscillate. So let's just go through each of these a little bit. And what we'll see shortly is exactly kind of where those patterns of electricity that or of current that we saw actually come from. So AC to AC. This is called a transformer. And the basic idea here is you have two coils of wire around a magnet. That's the simple version here. And what it does is, this is just like kind of how a generator works. Remember, it had the magnet and generator had a bunch of coils of wire around it, and we would create current through that generator, and that would create a magnetic field. Sorry, a current through that wire, and that would create a magnetic field. And a transformer is just like that. We have as input, on the inside, we have a bunch of loops around a magnet. So we send a current through here. This will create a magnetic field through this magnet. On the other side, we have a bunch more coils of wire around this magnet. And of course, this magnetic field around this, that's going through this magnet, will create current going out the output wire. The important thing is that the actual amount of current, or the voltage, I guess I'll say, you can go either way, really. You can call it both the voltage and current are proportional in the same manner. But what I write here is that the voltage scaling, how the voltage in these wires changes, is proportional to the number of loops around the actual magnet. Right? So if you have more loops of the wire on the magnet, that'll create a stronger, or not a stronger magnetic field, but basically, if you have more loops around it and the same magnetic field, that'll create a higher voltage coming out. Right? So the ratio of these two voltages, the input voltage to the output voltage, is just going to be equal to the ratio of the number of turns around this magnet of each wire. So by doing this, we can change the voltage from the input to the output. Now, of course, we're not creating power here. So if we step up the voltage, what's going to happen here is that the current going through this output wire will actually come down. It's a really simple relationship too, right? It's just that the voltage on the input over the voltage in the output equals the number of turns in the first one in the input divided by the number of turns in the output, which just equals the inverse ratio of the current. So power is preserved here, right? Because this times this equals that times that. Sorry, I should make that clear. V1 times I1 equals V2 times I2 here. But we have effectively changed the voltage and current. This is a very nice thing for a lot of reasons. The biggest nicety of this is that what really causes loss in a wire is not power. It's actually the current flowing through it. Current is the actual amount of charge that's flowing through that wire. And the losses you get from that wire are going to be proportional to the current flowing through it. In fact, that just comes from Ohm's law, right? Ohm's law says V equals IR. Depends on what you talk about power here. But power, remember, in this case, when I write power like this, power would actually be the power that's being lost in the wire when the resistance is the resistance of the wire itself. So remember, power equals voltage times, or rather, power, I'll just write it like this. Power equals current times voltage, which equals current squared times the resistance. So if you have very high current here, this expression just is actually for the power that's being dissipated in the wire itself when the resistance is the resistance of that wire itself. It's not if you have some resistance that's kind of at the end of your load here. What I'm writing here is the actual resistance of the actual wire itself. And so there's this common expression that I squared R losses, people call them, essentially. Your loss that you have, the power that you're sort of using up in that transmission, is going to be proportional to your current squared times the resistance. Right? So current in general is something you don't want. You don't want to have high current in big voltage lines because that'll cause a lot of power to just be burnt up in that voltage line. What you can do instead is create voltage lines, transmission lines, that have actually very low current. There isn't that much current flowing through them. So they're going to have actually very little losses in the wires themselves. And you do this by stepping up the voltage to be really high. You make the voltage really high. That has to bring the current down. And so on the transmission wires, you actually have very little current flowing. If we had those transmission wires at the same voltage as we have in the actual outputs here, that would be a disaster, because there would just be so much current that would need to flow through these wires, they would just, and you couldn't do it, they would burn up. And actually, this was a big reason why AC power back in the day was really took off. It's because there were these easy mechanisms for converting between AC and DC power. And one of the big original arguments for using AC power is the fact that we could step up the voltage for transmission, transmit it over very long distances, and then at the end side, step it back down to be at a point where it's safe for people to use. The danger, of course, is when you have high voltage, if you do close a circuit like that, that's a huge difference of potential energy, right? So that's very dangerous. You don't want to go touching high voltage wires. But the advantage is we can transmit AC power long distances without very much loss in the lines. Now, as you'll see in a second, we now have ways of actually doing similar transformations for DC. And so large-scale high-voltage DC is actually coming into its own right now. There's being a lot more infrastructure built that actually uses DC power, because there are actually good reasons for that as well. But when the system sort of came out originally, there were actually, we had much better ways of transforming AC power with much less losses, et cetera. And so this is a big reason why AC power really took off. Because it is kind of more complicated, right? You have to use complex numbers instead of just real numbers. So why would you want to do that if there wasn't some good reason to do it? I should mention that whenever you do something like this, there are going to be probably some losses in the system, right? And those will get, you might have some current that actually flows through this. You might have some loss in your magnetic field that isn't actually transferred into power here. And so transformers, a big, and you see them around, see those big little like garbage bucket looking things that sit on top of telephone poles? Those are transformers. They're stepping down power from maybe the grid level to something that actually can be sent out to all the homes themselves. And they do have losses in them, and those usually come in the form of heat. So this sort of, we're getting very good, and they're very efficient in practice, but we don't want to get sort of too, you have to be careful about building transformers, because there is some loss. If you start putting a whole lot of power through a transformer, it can overheat, and they can then explode, and that's bad for everyone. This is actually a big issue more and more now, where there are more and more, say, electric cars that are being used by people, and so all of a sudden they have much more power consumption than the utilities ever thought that homes would, especially in the night, right, where they think there's going to be very little consumption. And so oftentimes, if you get, are on a block where everyone buys an electric car, you have to think about actually upgrading your transformers on that block to actually prevent things from overheating and kind of blowing up. So kind of an interesting issue that comes up as people get these electric cars, which are more efficient and can be more sustainable, et cetera. You have to think about changing the infrastructure to account for these things. Now, in a circuit diagram, we draw a transformer like this. And it's really just a sort of symbol for two inductors, which kind of makes sense, right? Because inductors are coils of wire that you use to resist change in current. And a transformer is just two coils of wire right next to each other that happen to have a magnet between them. So we use this symbol, which is kind of indicative of these two inductors. And you usually write the number of turns as a ratio above the transformer. As I said before, they're going to have some resistive losses. So you're going to have there's going to be some heat loss for these things. In the ideal case, we think of them as just the ability to directly transform voltage, directly step up or step down the voltage. But in practice, there's also going to be some resistance to this element here. Finally, what I showed here was a single-phase transformer. Right? I'm talking about a single amount of AC power coming in and transforming to some other single phase of AC power. It's actually in phase with the input, but just has a different magnitude of voltage and current. you can also, but remember sort of the idea of three-phase power we talked about last time was that we didn't want to have basically inputs and returns for every different wire. And so this looks like you need some sort of input and return for every wire again. But it turns out you can, and you will on the homework, create a transformer that directly transforms three-phase power too. So you can have a transformer that has as input just the three phases of power, and as output three other phases of power where the voltage and current are stepped up or down. And you do that by combining single-phase transformers in something like one of those delta or Y configurations that I talked about last time. And you'll figure out how to do that on the homework coming up. But the advantage here is, again, we can have transformers where we only need those three lines. We don't need any more than that still. All right. The next element is the rectifier. Rectifiers, remember, were how we went from AC to DC power. And as we will see in a second, this is what causes those weird patterns in electricity that you saw, those little spikes. Those are caused by rectifiers. Now, the basic element of a rectifier is the first nonlinear element we're going to encounter in this class, which is a diode. A diode, unlike a resistor, inductor, or capacitor, if you put an AC current into this, or AC voltage into this, what will come out is not a sinusoidal current waveform. Because a diode allows current to only flow in one direction. So current can only flow this direction. It can't flow back. And then the little symbol we use to kind of denote that is an arrow with a little bar after it. So again, current can flow this way, but it can't flow that way. So the idea of DC systems is that we want power to kind of be always at some positive level. So we want voltage to always be at some positive level. We don't want it to oscillate back and forth. And the simplest way of doing that, actually, is just with a diode. So what we can do is we can just take an AC voltage source and just put a diode on it. What will happen here is when this voltage is higher than that, current will flow around this way, and will flow through the resistor going this way. But when the voltage is actually negative here and positive here, current wants to flow like this, or would want to flow like this, but the diode blocks it. And so from the perspective of the circuit, when the current wants to flow this way, this looks like it's an open circuit there. So no current will flow whenever this voltage down here is higher than this voltage up here. And we can, again, in our nice simulation packages we have, we can simulate things like this. So let's see, I had opened all these. Let's look at the half-wave rectifier. So this little symbol here, or this little circuit here, is what's called a half-wave rectifier. Because what it does is it basically takes it gets you kind of half the current you would get otherwise, right? Because you get it when it goes this way, and you just don't get it when it goes that way. And what this capacitor here does, actually, is it actually stores power. Capacitors we thought of as, or stores really charge, but we'll just think of it as, stores charge, not stores power. But it stores energy. And so when this side is bigger than that side, what will happen is that you'll have flow going through this, but you'll also charge up this capacitor. So it builds up a charge here. Then, when this is actually more positive than that one, and current can't flow around this way, what will happen instead is actually the capacitor will provide electricity for this element here. And so you actually will get, if you have a big enough capacitor here, you will get current flowing through this element the whole time, even when this is going the other way. So what the rectifier does in some sense is it first kind of chops off half of the voltage waveform or current waveform, and then uses a capacitor to kind of just smooth out the rest of that. So you do see kind of like a constant amount of voltage there. So let's take a look at what this looks like. in our wonderful simulator that we use. I had two there, I realized, but okay. So let's see what this looks like. So here is our little circuit we've built with a voltage source, and then a diode here, then a resistive load here. I probably shouldn't have given away what it looks like. But for simulating things like this, nonlinear circuit elements, we actually need yet one more piece of tools, or yet one more type of simulation for our simulator Quux here. We need a transient simulation. So remember, in our little set of components which we're going to look at for the homework, there are DC simulations, AC simulations, which we'll use primarily, but there's also the ability to simulate transient simulations, where actually you look at the actual waveforms that go in and out. And for a setting like this, where you have nonlinear elements, you really have to do that, because AC steady state doesn't really make sense when you have when you're chopping up this waveform so that it is no longer a sine wave anymore. Okay, so what does this actually look like? I'm going to just run the simulation here. And what we see here is what's essentially happened is that the voltage that this guy sees is essentially chopped off here. We see the positive portion of it, but we don't see the negative portion. Right? And right here, there's no capacitor, so it's not being smoothed at all. So it's just seeing only sort of the voltage when it's positive like this. When it's negative, this looks like an open circuit there, so it's not seeing any difference across this bit here. Of course, there would be a difference across this bit, but across here, it's not seeing any difference. Okay, so now let's put in our capacitor and see what happens. I should forget the amount of capacitance it needs here, but we'll play around with different values. Let's try 10 millifarads. This takes a lot longer to simulate now, because it's actually kind of complex. It has to sort of simulate through every step of this actual system. And let's see if I got it right here. Yeah. So approximately. So there's always going to be actually a little bit of ripple here, because you can never quite completely flatten out a signal. But with a big enough capacitor, you can do pretty well. You can sort of store enough charge that it's going to see, approximately the same amount this whole time. Okay, so what's happening here? What's happening is that this capacitor, when current is flowing around here, it flows through the resistor here, but also builds up a charge on this plate here. Then when we shut this off, so it's trying to flow the other way, we can still have current flow around this way, because this has built up positive charge and this has built up negative charge. So the capacitor will store this energy and provide it to the resistor when this rectifier is blocking the actual voltage source from providing energy. Now, the reason why this took longer to simulate than the other ones you saw is that the only way to simulate this really is to actually build the equations, the dynamical system equations of what's happening in this circuit. Remember, the capacitor, its law is that it relates the derivative of the current and the voltage. And so what happens is actually it sort of sets up a dynamical system that has all these elements in it, and then just steps through integrating this forward in time. And we'll talk actually later in the class about simulating dynamical systems, not so much in the context of simulating circuits, but in the context of simulating kind of bigger scale systems like the grid, and how you want to generate scheduled batteries, stuff like this. But this is just a dynamical system too, where you have to sort of step forward little bit by bit to actually figure out what's going on here. And so it takes longer to do, because this is what's actually going on here. Right? So look what we've done, right? We've taken an AC source, and what we get out on the end is a DC voltage. Again, it's not quite perfect DC. It isn't exactly flat, but it's good enough. And actually, by adding other elements here, like we can add an inductor too, which can smooth it in kind of a slightly different sense. And then we can also increase maybe the capacitance of this. We can get something that's arbitrarily close to a flat line there. Basically, depending on how much money we want to spend for these different components. You can get really, really close to a nice, perfect DC source. And in fact, most DC systems you have that you'll see can take voltage within some range here. And so having something like this that kind of has a little bit of jitter here is actually fine. Okay, any questions about this? All right, so I'm going to show in a second actually how this relates to what we saw in our little plot before. But before doing that, I'm actually going to just describe one more thing, which is this seems kind of inefficient, right, this half-wave rectifier, because we're essentially ignoring half of the signal, right? We're just throwing it out and saying we don't care about. Whenever the voltage is the other, it's sort of positive over here, negative here, we're just going to say we ignore it and not use that power at all. So a little more common thing is actually what's called a full-wave rectifier. And that's like this, but we actually have a little more complex system now. You need 4 diodes that manage to actually get power in both directions, but in a way that appears to be the same here. So let's see how this actually works. So let's suppose that this is positive and this is negative. Okay? So current can start flowing here. It can go through this way. It can't go this way, but it can go this way because we have the diodes aligned properly there. So current could flow here, could flow through that. Then here, it could flow this way, could flow that way, but we actually, is this right? Yeah, it wouldn't because the difference is there. And then it will flow back down here. So it would want to flow this way, not obviously right. It wouldn't want to flow this way because the potential is higher here than it is there. But it's lower than here than it is there, so it'll flow back around here. So when this is positive, this is negative, current will take this path here. So it's going this way through the resistor, following that path. In the other case, say this is positive and this is negative. Power will then do sort of make this the similar trip. It will go here. Sorry, not power, current. It will go here. Can't go this way. Go this way through the resistor. Again, go in the same direction through the resistor. Then back. Where did I go? Yeah. Then back up and over here. So the way these diodes are set up is in a way that actually allows current to flow regardless of which voltage here is higher or lower. Current will always flow this way through the resistor. And to get this, you need these 4 diodes set up here. So let's see what this looks like in our simulator. And now we'll finally get to this question of what's happening. Oops, what did I?
Would you still need the capacitor?
Yes. So that's actually a great question. I'll show you what happens here. So let's look at our. Oops, I opened the half wave again. Look at our full wave rectifier. Let's take out the capacitor at first. Also, let's hang on. Okay, so I'm not going to show the graphs yet. All right, so let's look at now. Here we have our full wave rectifier. And let's see what happens to this voltage here when we run it without a capacitor. So I'm going to add to our graph a graph of the voltage. That's just V dot dt. Okay, and I'll just run it also. All right. So what's happened here is that the voltage that sees here, we get it for every single phase. This little notch here, don't worry, it's actually just due to the fact that it's modeling that these diodes is not ideal diodes. They take a little bit of time before they can switch and allow some current to flow through, but after it's kind of built up on the other side. But essentially what's happening here is that, so it's actually modeling that, the fact that they're not ideal diodes here, this package. So what we see is what we expect, right? We see the fact that we see this voltage here that is always positive. So that means that it's always, we're putting a reference ground there. So it's always going to be higher here than it is down here. This side is referenced to 0. But for every phase, I mean, what's really happening is the current's going up and down here. But when the current's, sorry, the voltage source is going up and down here, when the voltage is positive here and negative here, we get this half of the wave here, and similarly the half. Now, when we don't have the capacitor, we get something like this still. So sometimes this is kind of better than the half-wave rectifier, because the half-wave rectifier just had this as being 0 here. So we weren't using that electricity at all. But we still probably wouldn't want to feed this signal into an electrical device, right? This is still not very well tempered to basically provide a constant voltage to that system. So let's add our capacitor again. I think I was doing it 10 millifarads again. So what we see here is actually the axis is scaled differently now, but it's only showing us the bit here that after this is settled in. But what's happening here is that by adding this capacitor, we have made this voltage more or less a constant DC source. Sorry, does this make sense? The axes have changed here. I decided to change the axis here. This goes from now 7 to 8. Before it went from 0 to 10. So now this goes from 7 to 8. We'd essentially smooth that using the capacitor. Okay? So now the big finale here is that what if we want to look at the current that's actually flowing up here? Well, this is what we did with our wire, right? Look at the current flowing through here. What does that look like? That's the experiment we ran before showing you this, right? So now I'm putting this current probe. I guess I already put it there, but I'm going to put a current probe near the voltage source, not near the end here, because this is already kind of DC power. I mean, A, we need a different type of current probe. We couldn't use our current transformer here. And B, I mean, the current flowing through here with everything smoothed out should be kind of constant, right? It should sort of, we just have a more or less DC system here. This current should be kind of more or less constant. But what does the current look like up here, coming out of the actual AC source? How does that draw current? So let's plot that finally. Look at the current. First delete this one. Look at the current flowing through that. Okay, so that's the current. And this is exactly what we saw in our plot before. These spikes then settle down. Now what's happening here is the following. This capacitor, remember, stores charge. Okay? So during one cycle, say it's gone through a cycle, it was putting power this way, and this has built up some positive charge. The source switches, and so we want a situation where we're providing power that would flow, I guess it would be this way, right? But initially, when this just becomes positive, the voltage here will actually be lower than the voltage that we have on our capacitor. So it won't flow that way. It would actually want to flow the other way, but it's being blocked by the rectifier, fortunately. So at first in the cycle, actually no current will flow from the source. All the current we get is being provided by our capacitor. At a certain point, though, this switches. And all of a sudden, in the waveform here, remember, the sort of the steady state it settled to was like 7 or 8 DC. So this will go higher than that. And when it goes higher, all of a sudden, it'll want to start drawing current, both to go through the load itself and to fill up the capacitor. So you'll start drawing current. Then you start kind of tapering this off. The capacitor starts filling up a little bit more. And so that causes this kind of thing to taper off more gently, up until the point where the capacitor, again, is higher charged than this voltage up here. When it goes the other way, the exact same thing happens, just in reverse, right? Because now this side goes positive. Current will still want to flow through this way due to the rectifier. But we have a system where it won't draw anything until it sort of reaches that cross point where the voltage goes higher than the voltage that's stored at this capacitor. And then it creates a big inrush. And so this is exactly what the kind of pattern you get from electronic devices that want a DC voltage source. Right? Remember, my iPhone here takes DC voltage. This guy really outputs, I think it's 5 volts DC voltage. So this here has this rectifier that actually will, from this, it also has actually a DC-DC converter which will step down the voltage to regulate it at 5 volts. But what it's doing is it's has this rectifier in here and a capacitor that changes that AC signal, we're getting the voltage signal, to a DC signal this phone can actually use. And same with the hard drive. The computers, the reason why it's a little different is because it actually has a lot more going on in there. The other thing is that when you start talking about very big loads, these things, type of patterns, can get really bad. And the reason for this, it has to do with our same sort of issues of things like real and reactive power. Now, it's sort of not quite clear what power really means, what reactive power really means in this setting, right? You don't have a sinusoid anymore, so what does it really mean to talk about reactive power? But there's similar issues you have with things like power factor and stuff like that. So from a utility standpoint, they don't like the fact that you're, say, drawing no current at all, and all of a sudden we draw a ton of current from them in their waveform, then stop entirely. Because the peak here, for example, will be a lot bigger than the peak you would draw otherwise. I mean, to provide the same amount of power, you're drawing a whole lot more current there. When you have these I squared R laws, this is kind of bad. So actually, a lot of devices have built in, even if they use something like this internally, they have built in some other storage source, maybe a capacitor up here on the actual AC system, or actually at different places in the system. That's not quite right. But they have other capacitors that kind of store energy at other points during this cycle to actually look more like a sine wave than something like this. But almost all electronics in them have something, and certainly like the cheaper ones you saw, like the hard drive with this sort of cheap power source here, looks very similar. This fancy power source here has a little bit more it can do than just this. But these little small ones have just these rectifiers in them. So again, this is all kind of strange, right? Because you think of AC power as having these sinusoids, and the utility provides a AC voltage source, or rather a power source really, and we'll talk about that in a second. But provides some power with the sinusoidal voltage. It has things like voltage and current that it draws, and it stays in some sinusoidal pattern. People still talk about reactive power, real reactive power at the grid scale. Yet what's interesting is that at the actual level of small devices like this, these look nothing like sinusoidal currents anymore. So, and this is why, these AC to DC conversions. Okay, so time we have left, I just want to get, I don't have demos for these last two. If you want to play around, yeah, what was that?
Is this a phenomenon that's like specific to electronics, or if you look at like a washer dryer or
right,
would you see something?
You will not. You will see something that looks much more like an AC current waveform.
So with respect to consumption at homes, it may be the case that this is not the dominant.
Yeah. So usually for a lot of big devices, something like a dryer, which is a big resistor, basically, if you have an electric dryer, those definitely can be more predominant, those loads. But electronics are becoming more and more prevalent in homes, and things like computers and TVs actually, especially because of the fact that they're always on, right? This is sort of these always on power consumers. These are becoming a bigger and bigger portion of home power. And so a lot of the work I do actually is with measuring power, monitoring power in homes, looking at what those waveforms actually look like. And if you look at just the whole home waveform in a building, in my experience, those very rarely look anything like a sinusoid, most of the time. They are sometimes, when you have, say, a dryer on, maybe. But even things like the motor in the dryer, it probably has some reactive power to it. So still maybe sinusoidal, but it's a little bit different. And then you see those little spikes all the time when you look at home current signals. So they are not negligible. You can't just forget about them and assume it's all fine. They do definitely occur in practice. And there is more and more, I think, at least at bigger buildings, there's more and more efforts put in place to take waveforms like that and transform them back to sine waves. So this is sort of the same thing you had with, we call them unity power factor devices, right? Things that for maybe motors, things that use a lot of reactive power, you'd want a device that kind of shifts that back to make it look more like real power. So using a lot of capacitors. That does look like real power from the utility side. So you're using the capacitors locally to provide you with reactive power, essentially. You can do similar things for these other waveforms. You have to do them in nonlinear ways. You basically use power electronics to do the inverse of these operations, oftentimes, to kind of, store power in nonlinear ways that depend on the actual waveform itself. But you can do that too, and that is more common. Certainly on large loads where you have maybe maybe like in a data center or something like that, where you have massive amounts of DC power that are needed. Those things are becoming more common. Yeah?
Doesn't the electronic dryer need constant voltage too? Or
Electronic dryer?
Yeah, because you said it would look more sinusoidal.
Yeah, the electric dryer, no. So electric dryers just have a big resistor, right? So you can think of that like a light bulb. You can put AC current through a light bulb and you don't notice anything different about it because the heat is actually what builds up, and so even though the voltage is going back and forth, it's still generating heat both ways. Heat has enough mass to sort of keep going. If you had maybe 1 hertz AC voltage here, you would see flickering, but you don't even see flickering with something like this. The power goes through both ways because the light comes from heat in this case in a light bulb. You don't notice the fact that it's changing back and forth because the heat sort of is kind of like a capacitor the filament here is kind of like a capacitor for heat. That's a poor analogy. Don't use that analogy. But because it is a resistor, in fact. But the same goes with the dryer. I mean, you have a big resistor in it. You don't need to care about which direction current's flowing through that. That thing will just stay hot, and it stays hot even if you turn off power for a second. So it certainly stays plenty hot from one way to the other of AC current flowing through it.
So like for your iPhone.
That's important because I wouldn't want you. Yeah, for little electronic circuits, those really need DC power. And you need DC power at a very high frequency, right? They're using the power here for logic, right? So they're using it for actual microelectronics. We're not going to talk about that at all today, or in this class at all, really. But those actually using DC power to represent digital components, and they really need a DC source for that because you can't have power going back and forth and figuring out what this is. I mean, maybe you could design a circuit that would work that way, but it wouldn't matter, because use 60 hertz AC power or AC current to power something like that. That would be pretty tough. It's much easier just to use DC there because the clock cycle of this is in the gigahertz range, right? So we're talking about very, very fast changes. You really need DC power for that. You need a DC source for something like that. Yeah.
Back to the light bulb, because you showed a bunch of them at the beginning.
Yes.
Before I had an understanding of what was going on.
Mm-hmm.
So what was the shape for the light bulb, for the LED light bulb?
The LED actually looked very similar to this light bulb, and that is out of, I believe it actually is, they do that intentionally.
But it wasn't it wasn't actually a sine wave, right?
It wasn't quite. It was like a cut off sine wave, right? So they have some amount. They probably actually. You know what? Let's get to the. We can keep talking about this. We can maybe get to the last 2 bits real quick in the next lecture. They're less important because we're not going to really talk about them too much. Let's maybe actually just see that again. So if we have this rectifier here and we don't have the capacitor. So say our electronics can use different. It still needs a DC source, but say it can use actually different voltages a lot more. Or maybe we just have a lot less of a capacitance here. So let's make this 10 microfarads instead. It looks much more like this, but there's this little time. The diodes block it for a little bit of time, but it has some sort of waveform like this. I believe that this guy looked kind of similar to that. So let's look at what this looks like actually. fire this all up, see if it works again. Oops, I started editing it. Okay, let's give it a shot. Okay, so this is the hard drive again. Here is the light bulb. Okay, so it looks something a lot like the sine wave, and there's some noise, and there probably is some power electronics in there that are doing, they might actually be shaping it something like that, but this looks similar to a rectifier that basically has much less capacitance, so it doesn't need as steady a voltage source. It can make use of different amounts of voltage. I can check that. I'm not sure that's actually what's going on here. It might alternatively be actually shaping this to look more like a sine wave, because that's, again, a good thing for large consumers of power to do. But this looks like what you would see if you just have that rectifier without a very big capacitor on it. So always going one direction through it, but taking different amounts of voltage.
Okay, yeah, the one more thing, that like the LED stands for light emitting diode.
Yes.
Right? So is it? I don't know how these are constructed, but could it be the case that the diodes in your circuit diagram are also the light emitting ones?
Oh, I don't know if they do it that way. I suspect I can look into that. I suspect they don't do it that way. I believe they typically, the light emitting diodes, they are typically more expensive than the ones that actually use this to rectify power. And so I would guess that they would actually put DC power through the diodes themselves, rather than try to rectify and do it at the same time. But I actually could be wrong about that. I actually am not sure about that. I'll confirm that, or I'll figure this out next time and mention it next time in class, because I'd be curious about that too, actually. Because this does look like a rectifier, just without any of the actual capacitors in there. So you could say just put a full wave rectifier, plop down, and get it to look like this. That's possible. I'll look into that, actually. But the actual light bulb itself just looked like a big resistor, right? That one made sense. Okay. And then just again, these guys here looked like. Now we can see them again, knowing what these actually are doing. So this hard drive again, starting up again, looks like these diodes, right? Looks like these rectifiers. Here the disk is spinning, so there's something actually going else on here, and it's consuming a lot of power, so it just jump down, actually, and the disk is no longer spinning. Yeah.
I don't really understand, like, what's it doing when the current is like 0?
What's it doing when the current is 0?
Yeah, because like I saw like white.
Oh, so like this, you mean? Just here?
No, I mean when you plug it in.
Oh, it just takes a second to start up first. Basically, there's a switch in there that needs power. And there's a small amount of electronics that essentially turn on when it first gets power, that will then open up switches in here that actually make this thing really turn on. So basically, when you put in a DC signal, it won't immediately turn on. It'll turn on in a few seconds. And that's just sort of, it doesn't take very long, right? It's just, it needs to see that it has a charge first, and then a few switches go.
When the current is not 0, is the switch turning on and off?
When the current is 0,
The flat part of the curve.
oh, here?
Yeah.
Here, you mean?
Yeah.
No, this is the rectifier. This is caused by that rectifier. So this is exactly what we see before. So there's no switch here in this system. Let me put the capacitor back in. Let me close this. So this is a system where there's no switch involved. These are just rectifiers and capacitors here. I run this simulation, and what you get in the current waveform is exactly this.
Yeah, but it's like, if the current is 0, is the hard drive still working?
Yes, because the hard drive is seeing, so in the situation, the current flowing through the resistor is not 0 here. This is the current coming out of the wire itself. So this voltage here is always steady, and it's always equal, and so the current, if it has the same resistance, is always actually equal here. In fact, we could actually just do that. So let's actually just look at, let's put in a monitor. Let's see, probes. Let's put in a current probe over here. See what this one looks like. So let's look at the current flowing through. Oh, let's simulate it first. Let's look at the current flowing through the actual resistor here. What that looks like will be this. Okay, and notice the axis here is scale, so this is always a constant amount of current flowing through here. That's actually very important. The current that flows through here and the current going through the hard drive, that is a constant amount of DC current. So it is seeing it as if it's just hooked up to a battery. What's happening on the other end, on the wire end, which is where we're monitoring things, is different though. There will be times there where it's drawing no current, and what's happening there is the capacitor here is providing the current, and it's providing the voltage. And then there are times when this voltage swaps here, so this one becomes higher than that there, and then it draws all that inductive current. So absolutely, and that's very important actually, that the device is seeing a DC signal, a DC voltage source effectively. So it's seeing DC voltage, it will see therefore if it has a constant resistance, it'll see a constant amount of current, but what's happening in terms of the actual AC system is very different. That's a very different amount of power being consumed there. A different shape of how the power is being consumed.
So what would that graph look like if you took out the capacitor and made it a very...
So what we'll look at then is that, remember, what will happen here is you'll have a voltage here that is only the top half of these lines, right, of these sine waves. And so because this part here obeys Ohm's law, you'll see a current that looks exactly the same. So what you'll see is the current there looks just like the voltage there looked. The capacitor is essentially storing charge to maintain a constant DC voltage and therefore also DC current, approximately, subject to the little ripples.
So the reason why there's no negative part is because of the diodes?
Yeah, exactly, because current has to always flow this way through the resistor by this full wave rectifier, right? If this is positive, it'll go this way. If it's negative, it'll go this way, right? It still goes through here. So it always goes this way through the unit, and that means the current always was positive from that sensor's perspective. And then the way you make it a DC source approximately is you just smooth this with a capacitor there.
So this isn't considered constant current right now?
That is not a constant current, I would say. I mean, it's sort of as almost, right? What you call DC and AC kind of depends on your level of how much ripple you're willing to tolerate. I don't think many devices can tolerate that much ripple. Maybe those LEDs can actually. I'll check on that and see exactly how those are working. But I suspect they have something like this, and then the LED here. And by the way, like Christmas lights, LEDs don't have that. They just have a little diode that's right in line with the thing. They're a lot cheaper, right? But if you wave a Christmas light around, what you'll notice is it actually flickers. So it sort of strobes in and out. If you have an LED Christmas light, wave it around, and you'll see a little strobe effect. This you don't see that with this thing. Here, this looks pretty normal when you wave it around, right? You don't see any sort of flickering there. You will for a Christmas light. And the reason why is that this has an internal system that actually will get a constant amount of power flowing through that LED, or approximately constant, so it'll always be on. Versus the Christmas lights, they just put AC sources right through a diode. And when the power's going the other way, it won't pass through, so they'll flicker. And they'll turn on and off. Yeah, I think we're out of time, so maybe we can just come chat with me afterwards. But we'll talk more about the last two bits of power electronics next time, and then we'll go into power flow.
Once again, why utilities prefer sinusoidal?
Right. So essentially, let me just turn all this off.